Hello everyone, this is Bonnie here at Maplesoft. Today I'm talking about MapleSim API. So essentially what this is a way to programmatically interrogate our MapleSim model or do analysis on it via Maple. And we're going to learn some of the key commands for doing that, and then I'll also show several examples, application examples of what we can do with MapleSim models, the different types of analysis we do, deeper beyond what we can do with standard MapleSim templates. So the first model I'm going to show is a very simple resistor, as you can see on the screen. I've added one single probe, and it's a voltage input. So let me just run this so we can have a look at the simulation results. Okay, so here we see our current through the circuit and also our voltage across the capacitor. So here we have a very simple model. What I'm going to do with it is attach a worksheet, a Maple worksheet. So now we're in the Maple environment. Automatically, you'll see that we have a MapleSim component that's automatically generated in this worksheet, and it will show whatever is in our model on the MapleSim side. So there's a live link here between what we see on the screen here and the changes being made here. So if I make any change here, I should be able to see that reflected immediately. You can see. And then right below that, you'll see the first line, MapleSim link model. So this is the first command and a very commonly used command in order to link the MapleSim model onto this actual Maple template. So if I execute this command, the model is linked. So the results were suppressed, so we didn't see anything. If I just unsuppress my results, you can see it says it is connected through the embedded component simulation 0, which is this component here. So just by doing that, our model is connected. So different things we can do with this now that it's connected. So what this means here, this is the main command, MapleSim :link model, and I've saved it as the module A. That's the name of my module. So now if I want to interrogate this module A, I can say, I can do different things. So the first thing I'm going to show is how we can extract the parameters of our model. So you can see I'm typing get parameters. You can see the queue that shows I can do autocomplete. So if I execute this line now, you can see I have added an option, all params, which just specifies I want all the parameters of this model. And you can see all of the parameters being returned. So C1_C, that would be our component capacitor 1. And then underscore C, so C is the parameter capacitance. And so on. So R1_R would be our resistor 1 and then resistance. And then it gives us the default value. So these values are just pulled in from the MapleSim model. Okay, another thing we can do, we can get the ports of our model. So, okay, so in this case here, because we don't have a subsystem, there are no actual ports associated with our model, or we don't have a subsystem, so there's no inputs, outputs. So by default, if we are on the main level, there will be no inputs. As you can see, this is null. Outputs will be considered everything that we've probed. So in this case, I have probed my current and my voltage. So you can see output is 2 elements here. If I go back to my MapleSim model and I create a subsystem or make my RLC circuit into a subsystem, so let's say collapse this down into a subsystem. If I double click on it again, I'll see my circuit again. And now if I go back to my Maple worksheet and I navigate to my RLC subsystem, so this time I'm saying I want to link this subsystem. I run this again. This time if I do execute my get ports command again, you'll see I have one input and no output. So as you can see here, I have one arrow in, so that's my input voltage, and then I have no outputs. If I wanted the same current and voltage output in this case, I would actually attach a current and voltage sensor and generate a port attached to the subsystem, and then I will get a voltage as an input and also my voltage and current as output. So let me just change that back. So I don't want the subsystem. And then one more thing we can do, of course, get equations. So this is similar to what the equations that we would get basically from our equations template. Actually, let me just do this here. So get equations. So you can see we have 2 equations generated here. There are, of course, different options in here. Again, you can see that these equations right now don't include the parameters that I've extracted here. So for example, my capacitance and my resistance, they don't show up here. And that's because all the parameters by default are numerically substituted into the equation. So the 24 was substituted into the equation. So if I want to keep those parameters symbolic and I want them to show up in my equation, to have a fully symbolic equation, I can specify what I want to keep symbolic by saying params equal. And here I just basically list all the parameters that I want to keep. So, and resistor. So I've included that, and now you can see that I have all 3 of these, R, L, and C. You'll also notice that right now I have 3 equations instead of 2, as I had seen last time, and that's because the voltage is no longer directly substituted, so I get a piecewise, basically representing my step function here. Okay. And then another function I can do is, or another command I can call is a simulate. This will basically run the simulation of my MapleSim model just as it does in MapleSim. So you can see the exact same outputs, my current and voltage. The output by default is graphical, so it will be plots. We can also, of course, select output to be data points. We can also say I am only interested in a subset of these outputs, and I can indicate these things. So let's say I only want to look at the voltage. So I can say output equals, and I'm just going to go up here and grab this, copy and paste. So this time you can see I'm only looking at my voltage. And all of those options that I was typing in for each of these commands, these key commands, they are inside our the help, of course. So I'm just going to open it up to give you an idea of the different type of options that are available. So for example, here we were looking at a simulate. So simulate. So there's my calling sequence. I can specify my return type to be data points. I can specify parameter initial conditions. All of the simulation options that are available inside MapleSim I can also specify here. So things like the simulation runtime, the type of solver I'm using, and so on. Okay, so it's all documented in the help. And then one of the most useful commands is our get compiled proc. That basically is compiling the procedure, compiling the model into a procedure, and that becomes very useful when we're interested in doing analysis on the model and we want to run the model over and over and over again, making only changes in the parameters So if we do it through get compiled proc, we basically only compile the model once, and then we will only integrate through every single time, as opposed to compiling and integrating every single time. So it's much more computationally efficient. So to do this, the command is get compiled proc. I'm going to save it as cproc. That's what I'm going to name it. So cproc equals a : get compiled proc. Again, I'm going to specify what my output is. Okay, I'm going to use the same output, voltage. So you can see we've generated this cproc module. Now, if I want to actually run my compiled procedure, I can now just call it like any procedure in Maple. So I can say cproc, and this will now give me the data point. So I can double click on this matrix and see my results here. So first column by default is time, second column would be my first probe. If I have more probes or more outputs, they will be added accordingly. If I want to see this visually in a plot, I can of course just plot my data. And there we have basically the exact same plot as simulate. But again, noting the difference between simulate and get compiled proc. Get compiled proc being very useful when we want to run simulations multiple times without having to pay the price of recompiling every single time. Okay, so once we've generated this compiled procedure, it's generally good practice to interrogate it to make sure that we have indeed compiled the procedure correctly. So some of the things that can be done to interrogate the model are getting the outputs. So this is very much like our get ports. So basically, I'm going to get the outputs of my compiled procedure. And you can see that I have indeed one output, the voltage. I can also get my initial conditions, make sure that looks right. And also parameters. So in this case, you'll notice that nothing was returned when I typed in get parameters. That's because in my compilation of the procedure, I didn't specify any parameters. That means this procedure right now, I cannot change any of those parameters. The parameter values are actually numerically substituted in already. So if we actually want to be able to change these parameters once we've compiled the procedure, we can add that in as an option. So let's say I'm going to call this cproc2. I'm going to make another compiled procedure. So get compiled proc again. Again, copying my output. And I'm going to also specify my parameters. I'm going to say I only want to keep one parameter symbolic, my capacitor. So again, I have my second procedure. This time, if I try to interrogate it and get the parameters back, we should be able to see, there we have it, a capacitor, or a capacitance value. So what we can do with it, once we have specified one parameter that we want to keep symbolic, is things like parameter sweep. So a parameter sweep, basically we're sweeping through a parameter through a range of values while maintaining all other parameters constant. And the goal here would be trying to evaluate the effect of one certain parameter on a certain output. So in this case, we want to look at the effect of, let's say, this capacitor on the voltage, current or voltage. So inside our MapleSim analysis package, we have a parameter sweep command. that we can use. So let me just type this in. So I'm going to call my results sweep. So I'm just storing this result. And then I'll call to our MapleSim library, analysis. The command name is parameter sweep. My arguments, my first argument is the compiled procedure. The second one is my parameter and also the range for the parameter. And then I can also specify other options, such as the number of points that I want to sweep through. So in this case, my procedure is cproc2. And then I want to sweep C from 0.01 to 1. And I'm going to say that I want my number of points between this range to be 10. So by default, the number of points is 5. I'm going to say I want a bit more. And I'm also going to specify my sampling time and also my TF. So that's simulation time to be 50 seconds. And you saw how fast that was to run that simulation. So now, in order to get the results, just going to do a plot command. And there we have our parameter sweep. Now, of course, with the plot command, we can add other options like legend so that we can see what color corresponds to which C value or capacitance value. But this shows very quickly one of the applications for these type of API commands. So this basically goes through the basic API commands. Now I'm going to go back to MapleSim and open up a few more models to show different applications for it. So this one here is an optimization example. Here I have a double mass spring damper system. The situation here is that there is a building with a dance floor, so the floor is being represented by a mass spring damper system. And we have people dancing on it at a certain frequency. So this is applying force onto the floor. And we're getting a lot of vibration from that. So the goal of this exercise is to add another mass spring damper to try to attenuate that vibration. So I have my MapleSim model. I'm going to open up a worksheet. Okay. So again, you can see the same setup. I'm linking my model, compiling the procedure. Compiling the procedure, and this time I want to keep two parameters symbolic. Basically, my spring and damping constants of the extra mass spring damper system that I'm going to add. And ultimately, what I want to do is get the optimal value for these spring and damping constants in order to minimize the vibration. So here is just a plot of before. So you can see basically, let me just expand this plot. So big oscillations. Here I've defined an objective function. So basically I want to minimize this objective function. And then I'm calling the optimization package within Maple. And I'm going to say I want to minimize the objective function using nonlinear simplex. And you can see the objective function includes the cproc with the parameters C and D, which is the spring and damping constants. So what it returns is the minimum value and also my two optimal solutions, so my spring and damping values. So if I pull these results back out and I push it into cproc to run another simulation with my new values, I get my after results. And you can see the vibration being attenuated. So after we do something like this, we can, of course, also push these values back out to MapleSim. So I can use, I've shown get parameters. We also have a command called set parameters, which is basically setting the parameters, so pushing it back out. So if I go back into our MapleSim model, you can see that these parameters are pushed out back into our MapleSim model automatically. So that was the optimization example. The next one is frequency analysis. So here we have a shaft. Let me just rewrite this. Shaft, imagine a shaft that's discretized into 3 portions, each with different torsional spring damper values and inertias. One end is fixed and the other end there's torque applied to it. Again, link model. So this time, because we want to do a frequency analysis, so I want to do a Fourier transform on the signal. I don't have to do the simulation over and over again, so I don't have to do a CPROC. So I can just use a simulate because I'm only running it one time. And I'm just plotting it out to make sure it looks right. And then I'm calling here our signal processing package to do our discretized Fourier transform. So I'm taking my RES is my results. I'm taking that signal and doing DFT on it. And then plotting my frequency magnitude plot. Okay, and finally, have an example using embedded components within Maple to interact with a MapleSim model. So in this case here, this is an electric magnetic buzzer example. So we have electric circuits, we have magnetics, we have a translational motion, and then a signals block. So we have a simple circuit. This is being translated to magnetic flux, translated to magnetic force or mechanical force. So there's a mass here that the magnetic force is pushing. A spring is pulling it back. The magnetic force is turned on or off depending on the position of this mass. So there's a position sensor here that's reading what the position of this mass is, and it will look at whether or not it has reached a threshold. If it does, it will open or close the circuit. And so in that way, the mass basically fluctuates back and forth very quickly, creating that buzzer effect. So going back into Maple here, again, link model. And compiling, oops, what happened there? Okay, compiling my procedure. This time I'm keeping 2 of my parameters symbolic. And then you can see I have a bunch of outputs, a bunch of things I'm interested in, things like current, flux, force, and so on. In this case here, I am plotting the position of the mass. And you can see that I have added embedded components, in this case sliders. We also have things like dials and text areas, checkbox, and things like that to make your application interactive. So here I'm using sliders to control my spring constant or my number of coils in the system. And you can see that the results or the mass's position is reflected immediately. So basically how we're doing that is behind each of these sliders, it's programmed such that it's grabbing the value and putting it back into the CPROC or the compiled procedure, and it runs it every single time I move this slider.